Let's look at a cycle that has a phase transition. It's called the Rankine cycle, and it's used in steam turbines where water is boiled to steam, sent through a turbine, and condensed back into liquid. This cycle has probably generated more usable work than any other cycle used by humankind. Let's follow 1 kilogram of water as it makes its way around this cycle. We'll start at this corner, which we'll call location 1. The first thing that happens to the water at location 1 is it goes through a pump. The water begins in a state of low pressure and low temperature. The action of the pump is merely to increase the pressure of the water. This doesn't require a lot of work from the pump because water is not very compressible. So we can model this as isochoric, or we can also model it fairly accurately as a transition of constant enthalpy. The actual word for this is isenthalpic. Great. Once the water is at location 2, it's now at a higher pressure. The water is able to flow into a boiler, and some fuel is burnt so that the water can absorb some heat. This heat absorption at first heats the water, but then the water begins to boil, and we transition from 100% water into 100% steam. It's possible for the boiler to continue to heat the water to above its boiling temperature, say 150, 200, 300 Celsius, by having additional fuel burners up in the steam region. We won't consider that for now. We might come back to it later. So we'll consider corner 3 to be here, and say that the motion on the PV diaphragm from 2 to 3 is an isobaric heating. Isobaric heating is very convenient because when there are no changes in pressure, we can associate the heat absorbed to the change in enthalpy, and we can look up the enthalpy on the steam table. Now that we're at corner 3, we have steam, 100%, that is very hot and very high pressure. It's ready to expand. So we send it through the turbine. The steam flows past the turbine, pushing on the vanes and turning the shaft. The rotational motion of this shaft is how we get our work output. This is connected usually to an electric generator. The expansion of the gas as it flows through the turbine is modeled as adiabatic. The slope of the adiabatic curve here will always be steeper than the slope of the phase transition envelope. So we go from pure steam at the start of the turbine to some mixture of steam and liquid water at the end of the turbine stage. So we'll say that the process of going from location 3 to location 4 is an adiabatic expansion. This adiabatic expansion is where all of the work of the cycle is generated. Our last step is to return the water back down to its initial state of being low pressure and low temperature. And we do this by a device called a condenser. The condenser basically puts the water and steam into contact with a cold reservoir. Usually we have some sort of coil set up that acts as a heat exchanger and a cooling fluid that can carry the heat away from the generator. The condenser is actually no more than a series of open pipes, though, through which the steam and water can flow. So it again is an isobaric process. Again, the isobaric process is very convenient because we can use the change in enthalpy values between location 4 and location 1 to get the heat ejected into the cold reservoir out through the condenser. Now let's do some sample calculations for this kind of cycle and see what goes into determining its work output and its efficiency. To define a cycle, we essentially need to choose the pressure values at location 1 and at location 3. I'm going to be convenient here and choose values that are in the table. Let's look at a Rankine cycle that operates between a low pressure of 10 megapascals and a high pressure of 20 megapascals. I'll now turn to the steam tables to find out everything I can about location 1. The temperature is 311 degrees Celsius. The enthalpy per kilogram, which I will label as H1, is given by the H sub F saturated liquid column under the enthalpy heading. The value is 1407.8. I'll save some time here by agreeing that all of my enthalpy values will be in units of kilojoules per kilogram. Let's now look at location 2. Location 2 will have a similar enthalpy value to location 1, since we approximate process from 1 to 2 as isenthalpic. For location 3, we can again turn to the steam tables for the pressure of 20 megapascals or 20,000 kilopascals. Here we see that the temperature is 365.75 degrees Celsius. And the enthalpy of the saturated vapor is 2,412.1. The other thing that we'll need to know about location 3 is its entropy. Because 3 and 4 are connected by an adiabatic step, they will have the same entropy. In the saturated vapor column for entropy, on the row for 20 megapascals, we see an entropy value of 4.931. Location 4 is in the mixture region, so we'll need to use the lever rule to determine its values. Our key is that location 4 has the same entropy as location 3 because this process from 3 to 4 is adiabatic. To use the lever rule, we'll need to know the entropy at location 1 and the entropy at a location which is not hit by the cycle, which I tend to call location 5. Location 5 is the fully saturated vapor, 100% steam, at the same pressure as location 1 and 4. This value occurs under the saturated vapor column under entropy for the row of 10,000 kilopascals. It is 5.616. The entropy at location 1 can be found in the same row, but for the saturated liquid of entropy column. It is 3.36. Using the lever rule with the entropy values, we can determine that the quality at location 4 is 0.6963. We now use this quality value again with the lever rule for enthalpies to determine the enthalpy at location 4. To do this, we need to look up the enthalpy at location 1, which we already have on the top of the board, but we also need to look up the enthalpy for location 5 from the steam tables. Going to the 10,000 kilopascals row and looking at the saturated vapor of enthalpy column, we get 2725.5. Using H5 and H1 with the lever rule for this quality value gives us an enthalpy for location 4 of 2325.3. Now that we have the enthalpy of location 1, 2, 3, and 4, we can take the difference of these enthalpies to calculate the heat absorbed and the heat ejected. The value for QH will be the difference in enthalpy between location 3 and location 2. That value comes out to 1004.3 kilojoules per kilogram. The value for the cold heat will be the enthalpy at location 4 minus the enthalpy at location 1. That comes out to 917.5 kilojoules per kilogram. The work is the difference between these two values. 86.8 kilojoules per kilogram. These numbers come out as kilojoules per kilogram because we're considering 1 kilogram of mass going around the cycle. If we want to know the actual power output of our generator in kilowatts, we need to multiply these by the amount of kilograms per second of water or steam that are flowing through any part of our pipe. Notice that this Rankine cycle, with my arbitrary choice of 10 and 20 megapascals, doesn't appear to be very efficient. In fact, we can calculate the efficiency value to be 0.086. If we compare this to the efficiency predicted by the thermodynamic limit, the Carnot limit, we would take our hot temperature, 365.75 degrees Celsius, converted to Kelvin, and our cold temperature, 311, and plug those into the efficiency formula for the Carnot engine. What we would get in that case is 0.086 to within a rounding. So it appears that even though this Rankine cycle involves constant pressure, and adiabatic steps, that its efficiency is very close to the efficiency of a Carnot cycle. But if we think a little bit more about that, our steps under phase transitions do actually occur at constant temperature. So a Rankine cycle exploits the property of a phase transition to have a constant temperature step, an adiabatic expansion, and another constant temperature step at the bottom. This means that it's very close actually to the Carnot cycle with 2 isothermal stages, 1 adiabatic stage, and the other stage that is isochloric. If we want to make our cycle more efficient overall, we would need to choose either a higher top pressure or a lower minimum pressure. Making the top pressure higher comes with certain risks. Boilers were well known to be dangerous in the past for having a risk of explosion. But we can also get a gain in efficiency simply by making the cold side of our cycle at a low pressure, sometimes even lower than atmospheric pressure, by using sealed pipes. Now let's discuss a slight modification to the Rankine cycle called superheating. In the superheating cycle, the pump step remains the same. But on the boiler step, we add additional heating that takes the system past the boiling point and superheats the steam to some temperature above its boiling point. This puts us at location 3 in the pure gas region. We still do an adiabatic expansion in the turbine on steps 3 to 4. And the condenser works the same, starting with some mixture of steam and water at location 4 and cooling isobarically back to the starting point, location 1. The difference of how we compute for a Rankine cycle with superheating is based on location 3. For location 3, we now have to look at table A6, the table for superheated water. Let's continue with the same pressures as our previous example, 20 megapascals for the top pressure and 10 for the bottom. Now on table A6, we need to look for the grid cell that has a pressure of 20 megapascals. I'll find this on page 921 in the top right corner. The superheating step now depends on an additional variable. How hot does the gas get after it's turned to 100% gas? We need to be told, in essence, the temperature at location 3. On the cell for pressure of 20 megapascals, we see that we are available to have temperatures between 400 Celsius and 1300 Celsius. Let's choose a moderate value of 600 Celsius for T3. The steam table A6 then tells us that at that temperature and at that pressure, steam would have an enthalpy of 3,539 and an entropy of 6.5075 in the appropriate units. This is the only thing that really changes in the analysis of the efficiency and the work output. The step from 3 to 4 is still adiabatic. So S4 and S3 are still the same. To find out the value of H4, we still use the lever rule between H1 and our additional location H5, which lies on the liquid vapor envelope at the same pressure as location 1. We can use the entropy value that we know from location 3 along with the values we look up for the entropy at location 1 and location 5 to figure out the quality X4, the percentage of liquid at location 4. We then use that quality value to determine the enthalpy at location 4 by using the lever rule again. The calculation of heats and efficiency and work works out in the same way as it did for the cycle without superheating.